So we've got, I've chosen these two topics just because they are two of the topics that appear on one or more of the tests next week. So infinite binomial expansion and vectors. I think vectors is on 3 out of the 5 tests, and infinite binomials on at least 2, if not 3. So chances are you're going to be having a look at it. So infinite binomial expansion is reasonably straightforward and procedural if you've got your handle on the formula. And the formula is given in the formula book. So just to kind of talk about the formula that I'm interested in, is if we have 1 plus x to the power of n, then we can approximate that using a binomial expansion using 1 plus nx plus n times n minus 1 over 2 factorial of x squared plus, and then it then kind of repeats n minus 1, n minus 2 divided by 3 factorial of x cubed, and then so on to infinity. Okay, it's an infinite binomial expansion simply because the powers that we tend to use this formula for are either fractions or negative numbers or both, that we can't use NCR to work out. So if we've got this expression here, 4 minus x to the power of a half, the first thing we're going to need to do is to make sure it's in the correct form. Now, this formula only works when the term in the a position, okay, is a 1. So this first term here has to be a 1. Now we can see straight away from this that this is not 1. So I'm going to rewrite this, okay? So I'm going to show that there's a quick way, and you can sort of skip to the end on this a little bit, but here's what we need to do. I'm going to take this 4 outside of the bracket, so I'm going to, factorize, which means that inside the bracket I now have a 1, because 4 multiplied by the 1 gives me 4, minus x over 4. Okay, so 4 multiplied by this minus x over 4 gives me my minus x. Now this is the whole thing that's being raised to the power of 1/2. Okay, and that makes perfect sense, hopefully. If you expand this bracket inside the square brackets, then you get 4 minus x. So then I'm going to look at the fact that 4 to the power of 1/2 is 2, and then I've got this. Okay, so this expression 4 minus x to the half can be simplified to this 2 brackets 1 minus x to x over 4 to the half. And now this is in a form that we can use our formula. So the first thing I'm going to do then is ignore the 2 for now. And I'm going to find the expansion of 1 minus x over 4 to the power of 1/2. I use my little wavy lines just because this is an approximation, because we're not going to write an infinite number of terms. And I'm going to do a direct substitution into the formula. So I've got 1 plus, and then n, which is 1/2, multiplied by x. And this is the key bit here. The x isn't just an x. It's whatever the b term is. Right? So the b term in this one is minus x over 4. So I'm multiplying this half by my x, which is minus x over 4. Okay, so 1 plus n times x. And then plus n times n minus 1, which is minus 1/2, divided by 2 factorial, and then x squared, which is also our minus x over 4 squared. Okay, see the pattern. So wherever you see an x in the formula, it's this minus x over 4 for our question. We're asked to do up to and including the terms of x squared. So this is the only one that we're interested in. So I'll just put plus dot 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 just to signify that this expansion does indeed go on forever. Next stage, I'm just going to take my direct substitution and simplify everything down. So 1, and then we've got 1/2 multiplied by minus x over 4 is going to be, pardon me, minus x over 8. And then I'm going to simplify this. 1/2 multiplied by minus 1/2 is minus 1/4. Divided by 2, 2 factorial, of course, is just 2. So minus 1/4 divided by 2 is minus 1/8. And then we've got minus x over 4 squared, which is going to be x squared over 16. And we're multiplying that by our minus 1 over 8. So 16 multiplied by 8, quickly on the calculator, just make sure I don't make any we usually got 128. So we've got minus x squared over 128 plus dot, dot, dot. Now, I did all that in my head and just checked it on a calculator, but you can literally, substitute these values in on a calculator and work them all out. So this is our expansion for 1 minus x over 4 to the power of a half. Now, we need to remember that actually we were multiplying that by 2 because that's what we were doing, right? That's how this 4 disappeared. We need to multiply by 2 at the end. So our expansion becomes 2 minus x over 4 minus x squared over 64 plus dot, dot, dot. Okay, so we've just multiplied everything by 2. So next, we have to state the set of values of x for which the expansion is valid. So the understanding behind this is that, I mean, if you were just to plonk any old number into this expansion and observe what happens, say, for example, we tried x equals 10. Okay? 1 minus 10 divided by 8, so 1 minus 5 over 4, minus 100 over 128. We keep getting away from 0, right? We're getting further and further away from 0, so it would be diverging, all right? And what we need this sequence to do is to converge. So we need to choose values of x that make each subsequent fraction in the expansion smaller and smaller and smaller and smaller and smaller, so that the effect that it's having on the expansion is negligible. And the way that we do it, the quick way I suppose to do it, is to take the term in the b position in the bracket, in our case it's this minus x over 4, and we're just going to say that this x over 4 has to be less than 1. And that's what's going to create successive terms that get smaller and smaller and smaller and smaller and smaller. Now, why haven't I used the negative here? Because I did say earlier that the negative was part of this. The reason is simply because when we do modulus, the negative becomes positive, so we don't actually need to put it in. So we just take this that's in the b position, in a modulus less than 1, and so then we simplify that down to this. We multiply both sides of our inequality by 4. So this expansion will work, i.e. it will converge on a single value if you choose an x value that is between minus 4 and 4. That's what this little inequality means. So that's part B done. So then part C is where things get interesting, I suppose. The whole point of the binomial expansion is, it was developed, it was proved in a time where calculators weren't the norm, all right? So if we did have to, say, for example, find the value of the square root of 399, then we'd have to find some numerical way of doing it, like a manual way of doing it. And the binomial expansion is the way that we would do it. Now, we're being told specifically that we need to use x equals 0.01. And so that means, the first thing that springs to mind is we could put x equals 0.01 into our expansion, right? That seems to be what the question's asking us to do. So if I substitute x equals 0.01 into my expansion, I get 2 minus 0.01 over 4 minus 0.01 squared over 64. And I can just work that out because that's the only bit we were asked to do up to and including the squared term. So I'll just do that on a calculator quickly. 2 minus 0.01 over 4 minus 0.01 squared over 64. And we get this number here. So we get 1.997. We're asked for 9 significant figures, so we've got 4 already. 1.997, 4984. Okay, 1, 2, 3, 4, 5, 6, 7, 8, and another one. 4 on the end because there's a 3, 8 on the end. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, 9 significant figures. There we go. Now, you can see from this is nowhere near the square root of 399 because, using our estimation skills, that's nearly 400, so we'd expect it to be nearly 20. So there's one other little thing that we can do using this x equals 0.01. using x equals 0.01, we can work out this 4 minus x to the power of a half, right? So we can say that's going to be 4 minus 0.01 to the power of a half, which is going to be the square root of 3.99. Now that's interesting because it's obviously very similar to what we're being asked to do. Now the square root of 3.99 is the same as this, isn't it? The square root of 399 divided by 100, which is 1/10 of the square root of 399. So we're sort of saying, if we substitute x equals 0.01 into this expression that we were given initially, we get 1/10 of the answer that we're looking for. So we take that and we say, right, well, if this is 1/10 of the square root of 399, it stands to reason. If I take my approximation given by the expansion and multiply it by 10, then I've got my approximation. Okay, so we can say, therefore, the square root of 399 is approximately 10 times this number, 1.997498444, which comes out as 19.9749844. And there we have it. Okay, we were expecting a number around about 20, or very close to 20, but just under, and that's what we've got. So this is, you know, the first two parts of this, A and B here, are very procedural. There's a formula, use the formula, you know, be careful with all your calculations, but then write down your expansion. State the set of values of x for which your expansion is valid. You always go to the thing that you expanded, you take this term in the B position, and you just put it in a modulus and make it less than 1. And then you simplify it, you rearrange it. Okay, so we got that as mod x is less than 4. And for part C, you know, in a way, I can't explain every single permutation that this question can take, but feel your way through it. If it says use x equals 0.01, use x equals 0.01 wherever you can. And there's only two places in this question that you can. It's in 4 minus x to the half, and it's in your expansion. Now, I didn't know that it was going to be, you know, to the point where we'd have to multiply everything by 10, but that's what appeared when I did the maths. All right, I didn't know where this question was going until I did something and then observed that these two things were equal. So what I'm going to do is, because I said I'd do 2 topics today, there is a second question for the binomial expansion, which I'll post in the general chat. Or if you're watching the video back, you can pause the video and have a go at. And I'll post the mark scheme for that a little bit later on today. But the second topic that I thought we could have a look at is to do with 3D vectors. Well, actually, as far as the tests go, I believe there's a mixture of vectors and 2D vectors on the tests next week. But all of the principles that you would do with 3D vectors are the same as those that you would do with 2D vectors. All right. So I've chosen 3D vectors just because arguably it's the more complicated of the two. But anything that you do, you can apply to 2D as well. So here we have some information about these vectors. We've got point A has position vector 3i plus 4j minus 2k. Point B, position vector minus 4i plus 7j plus 5k. Now, pretty much the first thing that I do whenever I work with vectors and i's, j's and k's is to write them as a column vector, just because I find them easier to work with. There's fewer letters, or no letters really, to deal with, and it makes life a lot easier, really. So 3, 4, minus 2, this is this vector here, 3, 4, minus 2. Why have I called it OA? Because the point A has a position vector, and position vectors are always to do with some reference point. And it can be quite useful to think of your kind of coordinate axes when you're doing this. So if you've got some x, y, z axes, the point A is somewhere floating in space, down here somewhere perhaps, and the line that joins up the origin with this point is described by the vector. 3 on the x-axis, 4 on the y-axis, minus 2 on the z-axis. All right? And that's why I call it OA. It's like a distance, sorry, not a distance, but the vector between the origin and your point A. So I'm going to do the same thing for B, the position vector of B. And I'm going to write it as a column vector again. So we've got minus 4, 7, 5. And part A of the question is asking us to find the vector AB. Now when you're doing the vector AB, if you were to think about it again, and I'll sort of remove this diagram, it's less useful for this, but say for example, here is my O, here's my A, and here's my B. OA is this vector, OB is this vector. What I'm being asked to work out is the vector from A to B. And how do I get there? Well, I go backwards along OA, I go forwards along OB. So essentially what I'm doing then is the vector OB minus the vector OA. Okay? This one forwards, this one backwards. The real, like, a shorthand for this, I suppose, is look at the second letter, look at the first, second minus first, B minus A. So we'll do that with our two vectors, minus 4, 7, 5, minus the 3, 4, minus 2. And it's just a straight subtraction, minus 4, minus 3, minus 7, 7 minus 4 is 3, 5 minus minus 2, 7. Now, for this question, and what I always tend to do with these is if the question is given in I's, J's, and K's, then you should write your answer in I's, J's, and K's. Okay, so I didn't use I's, J's, and K's until I wrote the answer down. Another note, I think it's good practice to put a little line underneath your vector letters, just because it denotes that there's a vector. Obviously, when they're printed on the page, they're in bold type, but we're not expecting people to do bold type. That would just get so messy, it's ridiculous. So I put a little line underneath, but you will not be marked down if you don't do that. Okay? So it's not something to worry too much about. So now we're going to find the magnitude of AB. And the magnitude of AB is simply Pythagoras theorem. Okay, so again, to use a simpler example, if we had a vector here and we had a vector there, how we find the distance between the two of them? We've got Pythagoras theorem. Okay, so we're going to use Pythagoras theorem to work this out. And it doesn't matter that we're using 3D vectors either, because it's just Pythagoras theorem in 3D. So we've got this minus 7 squared plus 3 squared plus 7 squared, which comes out as the square root of 49 plus 9, 58, plus 49, 107. So square root of 107. Check if it can be simplified. I don't think it can, that one actually. Might be wrong. No, root 107. And that's it. Okay, so that's our magnitude of a vector. Now, it could be that you're sitting there thinking, this is quite simple, why isn't it getting on to the hard questions? Because these OCA tests next week are, this is partly the kind of level that you're going to be doing questions on, all right? I can't, you know, but without giving anything away, these are the skills that we are testing. I would say you still have to revise geometric ones, like look at a picture where you've got to find or prove that the diagonals of a cube bisect or something like that. There's a few good ones in the textbook, so have a look at those as well. But these are the key skills that are being assessed in these tests. So there, yeah, so the last one really that I wanted to go through was just this, because I hadn't talked about the fact that when vectors are parallel, then one of them is a multiple of the other. So you can see in this question, P, Q, R, and S have position vectors like this. And we have to show that PQ is parallel to RS. So, you know, the first thing I'm going to write down is actually, I'm going to put all of these position vectors into columns. So OP is minus 3, 10, minus 7. OQ is 5, 4, 3. OR is minus 4, 6, minus 12. Now, you don't have to do this step if you don't want to, but I just always find it's easier to work with column vectors. So 8 minus 3, 3. There we have it. So we're to show that PQ is parallel to RS. Now that means we're going to need to work out the vector PQ. All right. Now remember from the previous question, if we're going to do PQ, then we're just going to do the vector OQ minus the vector OP. So we do 5, 4, 3, and we're going to subtract minus 3, 10, minus 7. 5 minus minus 3, we have an 8. 4 minus 10, we're going to have minus 6. And 3 minus minus 7, we're going to have 10. So there's PQ. And then we're going to have RS, which is going to be the vector OS minus the vector OR. So it's 8 minus 3, 3 minus 4, 6 minus 12, which is going to come out as 8 minus minus 4, which is 12, minus 3 minus 6, which is minus 9, and 3 minus minus 12, which is 15. And what you can see between the two vectors is that the vector PQ in every case is exactly 2/3 of the vector RS. All right, and I'm looking at each component individually. 8 is 2/3 of 12. Minus 6 is 2/3 of minus 9. 10 is 2/3 of 15. So PQ is 2/3 of S. Therefore, those vectors are parallel. And what does that mean? It means that they have exactly the same direction. All right. So for PQ, it goes 8 units along the x-axis, minus 6 on the y-axis, and 10 on the z-axis. However, RS goes 12 on the x-axis, minus 9 on the y-axis, and 15 on the z-axis. All right. So they are exactly the same direction. It's just that RS is longer. Now, you could be asked questions about describe the shape that this forms. And the common ones are, for example, a trapezium. You've got a trapezium if you have two parallel sides and one of them is longer than the other. Okay? You've got a parallelogram if you have two parallel sides of the same length, and then you've got another two parallel sides of the same length. Okay, so you might be asked to interpret this a little bit further in a kind of tricky part C of a question. But other than that, those are the kind of basic skills that are going to be assessed next week. So that's it for vectors, and that's it for the binomial expansion. I tried to do as many as I could within the kind of 25-30 minutes that we've got, so hopefully it was of use to you. And if it wasn't, I apologize. But good luck with your test next week. Anyway, I hope you all do brilliantly well. Look out for this second binomial expansion question in the chat in just a couple of minutes, and also the mark scheme for that a little bit later. Brilliant. Thanks, everyone.